Hello there. In this unit, we're going to learn all about chemical equilibrium. Now, chemical equilibrium is a whole bunch of reactions where the reaction can go in both directions. So you already know a few reactions like this, even though you may not have used the term. When you are breathing in air, the oxygen that's in your lungs goes through your alveolar membrane and into your blood, and it bonds to hemoglobin. And you get this complex of hemoglobin with four oxygen molecules stuck to the heme sites there where the iron is, right? And what happens then is that this reaction then goes in reverse, and the same oxygen gets dropped off when the hemoglobin and the red blood cells get to your body tissues. So in one part of the system, the reaction is going this direction and absorbing oxygen and creating this complex. And another part of the system, the reaction goes in the opposite direction and lets go of the oxygen at the tissues. So that is an equilibrium reaction because it is reversible, and it can reach a point where the reaction in one direction is the same as the reaction in the other direction, and that type of balance is equilibrium. So here's another way to represent this. You can have two different types of equilibrium. You can have one where it's static. Say you have two frogs sitting on a teeter-totter or seesaw here. If their mass is the same, the force downward will be the same, and these forces will balance each other out, and you can call that an equilibrium. There's a balance of forces. The other option is to have a whole bunch of frogs, and as long as the frogs can be moving, but as long as the same number of frogs are going one way as the frogs going the other way, it doesn't matter if the same frogs are on one side or the other side. This dynamic equilibrium, as long as the frogs are traveling in both directions at the same rate, then you can still have a balance. You'll still have the same number of frogs on both sides at any given moment because the exchange is the same in both directions. And so that's called dynamic when there's movement, and static is when there isn't. So a chemical reaction that follows this same pattern, like the frogs on the seesaw, is the reaction of nitrogen and hydrogen. This is called the Haber process because a German guy named, I think, Fritz Haber discovered how to do this in a lab and create ammonia. And ammonia can be made into all sorts of things from like explosives to fertilizers. And so a chemical reaction that kind of changed the world. Anyways, it's one of these reactions that can go in either direction. If you have lots of nitrogen and hydrogen, it'll produce ammonia. And then when there's more ammonia in the mixture, it'll go the other way and produce the hydrogen and nitrogen. And eventually get to a point where the rate in both directions is the same, and that is considered to be an equilibrium condition. So graphically, you can say that you start off with some nitrogen and some hydrogen, and as the reaction goes, you can see that it starts, quantities of those guys decrease, and the rate of reaction will decrease as the concentration decreases as well until it reaches the point where it's not changing. At the same time, as the ammonia is being produced, the reverse reaction is going to increase, right? So as more and more ammonia increases, the reverse reaction is going to get bigger and bigger. And eventually you get to a point where the reaction in the reverse direction will equal the reaction in the forward direction. And when the reaction going this way, that should be an H2, making NH3. When that is equal to the reaction going the other way, NH3 going to N2 and H2, we'll balance these out here. When the reaction, when one direction is equal to the reaction in the other direction, then you've got yourself an equilibrium condition. And you can use this neat double arrow here to represent that. I kind of like using the half arrow. Some people or some textbooks will use like whole arrows, but the little half arrows are easier. They kind of tuck up against each other neatly. Alrighty. So not all chemical changes or chemical reactions can produce an equilibrium. There are certain conditions that you're going to need in order for an equilibrium to be possible. First of all, you need a closed system, right? And so you can see this with a physical example of evaporation. So if you take this lid off and you leave this here long enough, all this water here is going to evaporate away, right? But if you close it, it doesn't mean evaporation doesn't happen. It just means that the concentration of the water in the space above where the water level is will eventually reach a concentration where you'll start to get condensation. And when the condensation rate is the same as the evaporation rate, well, you got yourself an equilibrium and no more of the water will evaporate, or it'll appear that the amount stays the same. But really, there's an exchange going on where the equal amount is evaporating as condensing, and therefore you have a balance. Reactions have to be reversible. It has to be possible to go in the other direction, and we're going to look a little more closely at that in a second. Temperature plays a part. Obviously, if you warm something up, you will get a different amount of water that evaporates into the space above this container. You all know that probably in the wintertime that you notice your hands are a little drier around the house, and that's because not as much water vapor can remain in the colder air. And that colder air, if it comes into your home, warms up, and then it starts to pull the water out of your skin, and that shifts that balance the other direction. So temperature does play a part for sure with equilibrium changes. And you have to have like measurable amounts of all the components, right? All the parts of the equilibrium have to be there. So that means you have to have some water as a gas and have to have some water as a liquid in order for there to be a true equilibrium. Have some on either side. Now, in order to decide if a reaction is reversible or not, or if it can be one of these equilibrium reactions, you got to look back at good old enthalpy and entropy, and that same little square that we did earlier on to determine if something was spontaneous or not can also tell you if equilibrium is possible or not. So let's consider the ones where equilibrium is not possible first of all. So first of all, if there's no reaction, then of course there's going to be no equilibrium. If you don't get any products being formed or any stuff on the right side of the equation being made, well then of course it's not going to go in the reverse direction either, so no equilibrium there. Now, a complete reaction is called quantitative reaction, and also in that case that means all of the stuff on the left hand side of the equation are going to end up on the right hand side of the equation, and you're not going to have any reactants left over. And so again, no equilibrium is possible under those conditions. But if the signs are the same, then you sort of have the enthalpy and the entropy sort of working in opposite directions against each other, and that means that equilibrium will be possible once those two values balance out in either direction. So you do have equilibrium here, equilibrium possible, and again down here, equilibrium is possible. So we'll be talking about these type of reactions in this unit. The other way to calculate equilibrium, whether equilibrium is happening or if the reaction is going to move in one direction or the other, is to calculate the Gibbs free energy. I'll skip to the end here. When the Gibbs free energy change is 0, that means you're at the equilibrium condition. And so you can think of like an ice cube in some water that's at 0 degrees Celsius, where you have some ice that's turning into water, and you also have some water that's turning into ice. So this is at 0 degrees Celsius. Now, if you raise the temperature there, that changes the entropy value, and you'd end up with negative delta G, which means it'd be going spontaneously in that direction, and you'll get the ice melting. And then if you decrease the temperature, then you're going to end up with a positive delta G, and the reaction will shift in the other direction, and the water will freeze. So at a given temperature, you can find the spot where the equilibrium will exist, and you'll get that balance of reactions in both directions. One misconception that students often have with equilibrium is that the quantities have to also be equal. There's an equal sounding word right in the name for it. But one thing to remember is that it's the rates, it's these arrows that are equal, the speed of the reaction in either direction. That's the part that's equal. The quantities don't have to be equal at all. So under one set of conditions, you might have a lot of matter on the left and very little on the right. But as long as there is a balance of reactions in either direction, then this is at equilibrium. And you can say that this type of equilibrium or this reaction will lie to the left because there's a lot more of the N2O4 in this particular reaction. Now it's left using the equation as it's written, right? So this is the left side here, this is the right side. If there's a lot more on the left side, you say it lies to the left. And then the second set of conditions, maybe the temperature changed or there was some other set of conditions that affected the equilibrium. And a new equilibrium was established, but this time there was way more on the right-hand side. You could say that this equilibrium lies to the right. Another neat thing about equilibrium reactions is that the proportions of the reactants and products, with the left side and the right side of the reaction, end up being the same regardless of how much of the reactants and products that you start with. So if you have the same number or same mass of the two components, and say you start with, in this case, the N2O4, which is my blue guy here, and you see it gets used up and you get some NO2 being used or produced in that same amount of time. Once the quantities stop changing, you are at equilibrium. There have been studies to show that there's still an exchange going on here, that the NO2 is still being turned into N2O4 and vice versa. Use radiation to show that this exchange is still occurring. And so just these constant steady levels, the steady concentrations that you have at equilibrium, are the result of equal exchange in both directions. Now you can start with lots of NO2, like the same number of moles of atoms, and end up with exactly the same equilibrium given enough time. So the reaction will shift in order to reach the same equilibrium regardless of the materials that you start with. If you start on this side, it's going to go that direction until it reaches equilibrium. If you started with the NO2, it's going to go in the other direction until it reaches equilibrium. As long as it's in a closed system and it's one of those equilibrium type reactions where it's possible, you'll end up with the same proportions. Finally, one useful tool in all of your equilibrium solving toolkit is the good old ICE table, where you change the meaning of the E. Rather than end, you can make it mean equilibrium. And instead of having one of these reactants go right to 0 as the limiting reagent, you can work out equilibrium quantities and use that to solve for other values. So in this case, you were given one of these equilibrium quantities, and you can see that the hydrogen decreased over time. So that's a negative change. If the hydrogen decreased, that means the nitrogen decreased as well. The reaction was shifting in this direction, which means you're going to end up with more ammonia over time. And then you can add in X here and the right proportions from the balanced equation. And you can use this here to solve for the X value. So 0.45 moles per liter minus the 3X is going to equal 0.30 moles per liter in the end. Your 3X then is going to equal 45 minus 30 is 0.15 moles per liter, and so X equals 0.05 moles per liter. Once you have X, you can sub that into the other two and end up with what the final amounts would be. So 0.45 minus the 0.05 is going to be 0.40 moles per liter. And over here, we're going to have 2 times the 0.05, so that's 0.10 moles per liter at equilibrium. So same process, you're just using equilibrium quantities, and you don't have to have one of them running out. Great, we'll see you soon.